multiply neutrons, this setup delivers a sudden burst of neutrons, enough to fission most of the uranium instantly. Since these are fast neutrons, even natural uranium, not enriched, can be used. This third stage greatly increases the bomb's overall explosive power. However, there is a serious drawback. Since the third stage is a fission reaction, it produces heavy radioactive fallout. That is why this design is used only when maximum destructive power is the main goal, with little regard for contamination. The United States' Castle Bravo test, with a yield of 15 megatons, is believed to have used a three-stage setup. The Soviet Union's Tsar Bomba, the largest nuclear explosion ever, had a yield of 50 megatons, half of its original 100 megaton design. The uranium tamper of the third stage was deliberately removed to reduce fallout. Modern nuclear weapon designs are even more advanced, often incorporating multiple stages. The initial fission trigger typically includes a fusion boost, and the third stage can contain a mix of both fission and fusion reactions. With such multi-stage configurations, we now possess the ability to scale nuclear weapons to almost unimaginable levels of destructive power. Whether we choose to do so, that remains a question not for science, but for the conscience of humanity. By now, you might have realized nuclear weapon is not the name of a single bomb. It refers to an entire category of weapons. And yes, there is more to come. Some are tailor-made for specific purposes. Others are designed to be extremely dirty. That brings us to the neutron bombs. Earlier, we saw that fusion reactions in hydrogen bombs produce a large number of free neutrons. In three-stage bombs, these neutrons are used to trigger an additional fission reaction. But what if the neutrons themselves were used as the main weapon? It may sound strange, but that is exactly what the neutron bomb was designed to do. Neutrons have a unique advantage. They are very hard to stop. While gamma rays can be blocked using dense materials like lead or thick concrete, neutrons behave differently. The reason lies in atomic structure. You might have heard that most of what we see as matter is actually empty space. This is because an atom consists of a dense nucleus at the center, surrounded by electrons orbiting around it. The space occupied by these electrons defines the overall size of the atom. But compared to that, the nucleus is incredibly tiny. If an atom were the size of a football stadium, the nucleus would be like a peanut at the center. That means most of the space we consider part of an atom is in fact empty. Still, this space is not easy to pass through. Electrons constantly occupy it and create a negative charge cloud. If another atom tries to enter, the charges repel each other. Even light, being electromagnetic, interacts with this charged space, which is why solid objects are opaque to it. But neutrons are neutral. The negative charge of the electron cloud does not affect them. In a solid object, atoms are packed so closely that even light cannot pass through. But to a neutron, the same solid appears as widely spaced nuclei floating in vast empty space. They are oblivious to the electron cloud. That is why neutrons can pass through thick materials like concrete or lead quite easily. This does not mean neutrons never interact. They can collide with nuclei along the way, but such interactions are rare, allowing them to travel much farther through matter than most other particles. This means neutrons can easily penetrate bunkers, fortified buildings, and armored vehicles like tanks, causing harm to the people inside. When a large number of neutrons pass through the human body, some collide with atomic nuclei in our tissues, leading to severe radiation damage. They can also make certain atoms temporarily radioactive, adding secondary radiation effects. So, the main damage from a neutron bomb is not from the explosion, it is from radiation. A neutron bomb is essentially a modified hydrogen bomb. Its explosive yield is minimized, while its neutron output is maximized. The goal is to kill living beings through radiation while causing minimal damage to buildings or equipment. Death may not be instantaneous. It can take hours or even days due to internal radiation damage. Because the fission stage in a neutron bomb is very small, radioactive fallout is limited. The secondary radiation from neutrons also decays quickly.